Good morning, students. So in the previous lecture we discussed about the concept that what is the particular process through which we can prove that there will be a Gaussian surface which is a closed one and also which follows symmetry, and we discussed about particularly some methods, like we said that the first test must be a Gaussian one, then it must be, that means it will be a closed one, it will follow symmetry in cases of charge and theta. So this is the basic part. So it must be a Gaussian one, it must be a closed one, it must have to maintain symmetry in case of charge and that of theta. Then we calculated in the case of by the what is the value of closed integral over E dot ds. Then we calculated total amount of q enclosed. This is the third method. Fourth, we applied Gauss theorem. So these are the four methods. We discussed that whenever we want to calculate the total amount of lines of forces as well as what is the expression for electric field, then we always calculated through this one. So now also what we are going to study, it is called the application of Gauss law. What is one? The Gauss theorem we studied. There are certain applications, because in Gauss theorem we gave or we discussed particularly about the concept of a sphere, which is normally we can see it as a symmetrical one, but let us consider there will be not a sphere, it will be a cylinder. That's it will be any kind of structure. Then how to calculate what is the total amount of electron inside it? So this is the basic part. These are the processes through which we need to go. So here the heading is electric field due to an infinite charge conductor. So see, when I am saying infinite one, it doesn't mean that the length will reach up to -2 plus infinite. It's like that if I will consider any conducting body which is containing certain charges. Clear? Then we are talking about some region, and this region as compared to the whole length is found to be much more smaller. Like if I will give the small example, consider this whole board. So this whole board has a particular area. So if I will consider that, what is the electric field? Let us I will talk about a small region, and I will take a small point here. Let us say here a small point outside the board, and I will consider the effect of this. Or if you will consider about this, let us consider the whole board, and whole board contains certain amount of charge. If I will consider a point is here, this one. So when I will talk about the effect of electric field due to this whole green board on this particular point, then you can see that for this point the board seems to be infinite. This is the basic case. So you need to be very much clear that when I am writing infinite charged conductor, it may be a straight line conductor, it may be a spherical one, like we already discussed about distribution of charges, lambda, that of sigma, that of rho. So the same structure will go on, like your one dimensional, two dimensional, three dimensional one, and also we will apply here also. So if you will talk about this point, so depending on or with respect to the whole structure of this whole area, the charges compressed by this particular board, this point seems to be very small. So for this point, the board seems to be infinite. This is the basic case. So in the same way, if we will talk about any kind of straight conductor, we will talk about some portion, and that some portion is considered to be very much smaller as compared to the whole length of the conductor. That's why it is considered to be infinite. So that is the considered point where we are talking about the effect. That considered point is too much smaller in dimension as compared to the whole structure of the conductor. What is one? So see. So now the first one is, when we talk about electric field due to an infinite charge conductor, here our case will come. So let us consider a straight conductor. So let me discuss the diagram first. Let us consider you are having a straight conductor which is being charged positively. And now our work is, as usual, we will take a point, let us say P, at a distance of, let us say, R from the conductor. So what we need to do? The first process was we need to find that it must be a Gaussian surface. You need to go through the previous lecture for this, if you don't remember the things. So the first it will be a Gaussian surface, and under this Gaussian surface we had a particular condition that it must be a closed one. Second one, it must be maintaining symmetry. So we will discuss about this one. Let us consider the point P is here. So what I will do, in this other direction also I will draw another point at the same distance, so that both sides the distance, let us, this will be also r. So in this way, if I will take another point here, another point here, another point here, the same way I will take the replica of those points here, here and here. If I will join them, then what I will get? If I will join them, then what I will get? Particularly this is a structure. Got this one? So always remember, for a straight conductor, the hypothetical symmetrical and symmetrically closed surface, which is called the Gaussian surface, is always found to be a particular cylinder. So here we will draw the cylinder particular. This is the basic case. So the region which we are considering here is very small as compared to whole length. The whole length of the conductor will be very high. That's why it is called an infinitely long conductor. Got this one? Okay, so we got the cases here. Particularly the first one, it satisfied that it is representing a closed surface and it is also symmetric. Symmetry means the electric field, which is the value of electric field here, must be same as here. Also the electric field which is have a value of here must be equal to here. So everywhere in this point, the electric field which are at a distance of r from the conducting body must contain your equal amount of electric field. Like for example, I will say, if I will talk about any region here, see this is a curved one. If I will show you this one, this structure I am talking about. So this is a curved one. Got some? This is a curved one. This structure. So see, this is one end, this is one end. The conductor is in between or inside it. So this curved surface, it is containing some region. So if I will consider that, let us consider the electric field is going towards you. So that the area vector which you will consider here for this particularly curved one, say you will get two flat surfaces, one curved one. So when the electric field is, let us say, going in this direction. See here what is happening, electric field is coming like this, coming out like this, coming out like this every time, because we already discussed in our linear charge distribution that the electric fields are coming to be in the parallel form. So electric field is coming in the positive x, also coming in the negative x, and no electric field is going up or down. That's why if you consider about this one, this is a cylinder, then the electric field is, let us say, going here in this direction, also coming here. So if I will consider any region here, then it must have area vector, and we know that area vector is always perpendicular to the surface. So if the electric field is like this, then the area vector also going like this. So here all the points on this curved surface, on this part, must maintain a value of theta equal to 0. So here see, it satisfies that it is a Gaussian surface, it is a closed one, and it contains symmetry. Symmetry with electric field and the angle. Electric field means all the points on this particular region is going to have or going to experience same electric field, and also with respect to the area vector, which can written as ds square, always theta is found to be 0 degree. This is the basic case. So it satisfies the first case that it must be a closed surface. It is going to follow the symmetry for electric field as well as for the angle. So this one here also the same thing will happen. Electric field is coming towards me, and the area vector which we will talk about, this will also perpendicular. That's why ds square and that of your electric field always makes an angle 0 degree. They must be parallel to each other. If you will talk about the upper flat one and the lower flat surface, this one, upper flat one and the lower flat one, then what we will see, that electric field is going like this. This one is the direction of electric field, or this one is the direction of electric field. In both the cases, if I will talk about any region here, electric field is going like this, going like this. Any region will going to come out towards you, so that this area vector and this electric field always going to be perpendicular. The same thing will happen in the downward also. Electric field is going here, coming here. Here is the area vector, so it will come out. So this area vector and electric field always found to be perpendicular. So this is the first case. So first case is being satisfied that it is a Gaussian surface in the form of a cylinder. It's closed one, and also it is symmetrical with respect to electric field and theta. That means effect or the value of electric field will be similar everywhere. Here also similar everywhere, and also the angle they are making. That means every point in these two portions are making an angle 0 degree with the electric field. Whereas here all the points are going to make an angle of 90 degree. Here also the same. That's why here they are maintaining symmetry by making angle 90 degree. Here they are maintaining symmetry by making angle 90 degree. In both these lines, they are also symmetrical by maintaining an angle of 0 degree. That's why it satisfies our first case or first step, that the cylindrical surface, or we can say the hypothetical cylindrical surface for a long straight conductor is a closed one. It is symmetrical to electric field in that of the angle. Got this one? So this is the first case which is satisfied. Clear? So we can write here a cylinder is the best symmetrical surface for a long conductor. You need to write these things in your example. What is also, this is the hypothetical cylindrical surface. Then we can write here like the structure follows. The structure follows symmetry as E and theta are same in every point. Got this part? This is the basic part. In every point, in the curved surface, the first case. That is, I told you, this is the curved one. Clear? In this curved surface, we are going to get everywhere the theta is found to be 0. With respect to whom? With respect to electric field. That is, theta equals to 0 degree. This is one case. Second case, the structure also maintains symmetry as E vector and theta are same in both the flat surfaces. In both the flat surfaces, that is theta is equal to how much? Will be 90 degree. So this is the proof of, this is the fulfillment of the condition for our symmetric concept. Got this one? So now we will go to this second step which we read. That means when we are proceeding to prove the expression for electric field in case of any kind of structure by using Gauss theorem, we have, this is the first process. They need to maintain the symmetry. Now we will go for the second one. The second one we calculated that we need to calculate what is the closed integration for E dot ds here. Clear? So we will get C. We will get here one will be get the curved one will be the upper flat, one will be the lower flat. Clear? So we will get the three expressions here. Okay. So the step 2 we will go to calculate what is the expression for our closed integration over E dot ds. Clear? Quite necessary concept. These are going to be important long questions many years in your board exams. Okay. So the second one, now calculating closed integration over E dot ds. So we have the formula that ds cos theta. So see, if I will draw this one, so what I will see, if the electric field is going like this is the electric field, this is the electric field, these are the directions of electric field, and here also you will get the directions of electric field are like this. These are the directions of electric field. That means they are coming out. Electric field here, electric field here. So now see, consider any region here, any area. Then what we will see, the area vector will always come out. So this is the area vector. Let us say ds cap. Here if we consider, this will be also coming out like this. This will be your ds cap. So everywhere you will find that the angle between electric field and the area vector of ds area is always found to be theta equals to 0 degree. Got this one? So you will get, these are for the curved one. Here let us say consider about any region. Let us, this is the area. Let us here this is the area. So what will happen? The electric field is going like this, And when the area vector, that means this is the flat one. You need to visualize this one. This is the flat one. So this flat one, like this. This flat one has an area here. So when you will draw area vector, it will come perpendicular. That means it will be perpendicular. So what we will get? The electric field and the area vector is 90 degree. The same thing will happen here also. Area vector will come out. Electric field is like this. So every time all the points on this upper and lower flat surface are going to make an angle of 90 degree with the electric field, whereas all the points on the curved one is going to make an angle of 0 degree. So this is the basic part of our calculation. So in case of our calculation, we will divide this integration into 3 parts. One will be curved one will be your flat surface one will be your flat surface 2. Okay. So now we need to write the expression. So write down integration over E dot ds equals to, so I can write C. The first surface I can write curve, then there will be addition. So here I what I can write D dot, let us say ds1 plus, here will be, let us say it will be your flat surface 1. Electric field will remain the same, only area vector will change, ds2 plus close integration over flat surface 2. Again it will be E dot ds3. So if you will calculate the value, now see E ds1 cos. So in this case all the curved surfaces, what we said, the theta is always found to be 0. So this will be your cos 0 degree plus flat one, it will be your E ds, angle is what, cos 90 plus integration over flat 2, it will be E ds cos 90, or both the flat surfaces having 90 degree electric field, whereas only the curved one is going to have a so what we will get, see, this will become 0, this will become 0, only this part remains. That means in case of an infinite long conductor, we got the Gaussian surface as a cylinder, and only the curved surface is going to contain the flux. Upper part doesn't have any kind of interference or any kind of presence of there in the case of our calculation of electric flux. So what we got from this one, so E dot ds is going to be your only E ds, or we can get normally right close E ds from here. This will become 1, so you will get E ds1. Clear? Got this one? So this is, you need to write this very clearly. In your books also you will get the same concept mathematically, but the theoretic part, the concept part you need to understand here. So see, now electric field is uniform for all the points, so it will be taken outside, and this will be your ds1. So see, ds1 means we are talking about any region on this curved surface. Got this one? So here we can write the total curve. We can write this one curve. So this is the region of the whole curved one. So when we will open it, got this one, then what we will get? This is in the this one, like this. This one, let us say its length is L. Its length is L. So what will happen when, let us say this one is the curved one, so it is in the form of a circle, so this will be 2 pi r, the length is L. So when I will open it up, it is like this, yes or no? So you will get 2 pi r into that of L, this is L, you will get the 2 pi r, the whole circumference of the circular part. So what you will get, it will be E multiplied by 2 pi r L. You know already, when you will open up a cylinder or by its curved surface, it will be like a structure going to a rectangle, when we are going to get the circumference as the length, and that of this L is as the width. Then we will multiply them. Clear? So this is the basic part. So what we got? Close integration of our E dot ds is equals to E times 2 pi rl. This is the second step we calculated. Now the third we need to calculate. What was that? We need to calculate total amount of charge enclosed inside the Gaussian surface. So this is the amount of charge enclosed. inside the Gaussian surface. Not the above one, not the down one, only this amount of charge. So see, here if you are, as we are talking about a straight line conductor, so this is in the form of a one-dimensional structure. As we know, then we will introduce the concept of your lambda, which is already be read as the concept of your charge distribution, or called as linear charge distribution, and the lambda is called your linear charge density. Got this one? So this is the basic one we will do. So now going for the step 3. So now for the step 3. So what was the step 3? Calculation of total charge Q enclosed inside the Gaussian surface. This is the basic part. You need to understand this one. Got this one? What is the amount of charge you are holding? This is the basic case. Okay. So now we will calculate. So as we have the formula, lambda is equals to Q upon L. That means the distribution of charge throughout the length. That is charge per length. You charge per unit length, which we consider to be your charge density. Then from here what we will get? Q equals to what? Lambda. So we got the total value of Q. It's not the long part. Got this one? Okay. Now the step 4 comes. Applying Gauss theorem. Applying Gauss theorem. Clear? Okay. So Gauss theorem we have, that is the closed integration over E dot ds is equals to 1 upon epsilon times the product of the whole charge, that is Q. So okay. So we will write the formula there. So what is the Gauss theorem says? Closed integration over E dot ds is equals to Q upon epsilon naught. So see, from the second process you got that E dot ds closed integration found to be E into 2 pi RL. You got this much? So we will put this value here. Then we will get the expression to Q. It is there, lambda L. Epsilon will remain like this. So if I will put this one, how much I will get? E times 2 pi RL equals to Q is your lambda L by epsilon naught. So L will be cancelled out. So we need to find the electric field. So it will be how much? Lambda by 2 pi R epsilon. So this is the expression for electric field in case of a long, straight, infinitely charged conductor. Got this one? So this is the basic case. So whenever you will get any kind of question regarding the applications of Gauss theorem, then you need to consider any kind of hypothetical structure. In your courses, there are 3 applications are there. One will be long, straight conductor. One will be infinitely flat surface or 2-dimensional surface. One will be your spherical one. So spherical one is not a problem because we already done that one. Next application we will read about the flat surface one. Then also we will calculate the same. One hypothetical closed Gaussian surface. So the process is this one. Always remember, the method is you need to draw first the Gaussian surface which needs to be closed. It needs to maintain the symmetry. Symmetry maintenance is the primary thing. It must have to have electric field in all the points similar. Also it's going to make the angle theta everywhere same. That's why the first step in all kind of applications of Gauss theorem, you need to proceed like this. First you need to find the Gaussian surface. It must be a closed one. Also it is going to be symmetrical with respect to electric field as well as the angle. The area vector makes with the electric field. Second, you need to find the value of closed integration over E dot ds. What is the value you will get according to the structure? Third, you will calculate the amount of charge enclosed inside that particular Gaussian surface. That is the third basic part. In case of a surface, you will get sigma. In case of volume, you will get rho. Not a problem. Charge distribution already taught to you. Then the fourth one, you will apply the Gauss theorem. Then you will, at the end, you will get the expression for your electric field. So for this line charge, we got the electric field is depending on C. Whom? Depending on lambda. It depending on your R. So till there will be no change of the distance from this straight line, there will be no change in the value because this is a constant, these two are all constant. So we only depends on lambda and that of the R. Got this one? This is the basic case. So there is no dependency of anything else. Clear? Okay, so this is the expression for electric field for a long straight conductor. E equals lambda upon 2 pi r epsilon.